Hi, my name is Michael Wong. Today, I'd like to talk about modern C++ heterogeneous programming with SYCL. First, a little bit about my company. I work at Codeplay, which is based in Edinburgh, Scotland, with around 80 staff, mostly engineers, working on open standards project. Our goal is to make AI and HPC open and safe to everyone by contributing to open standards and participating in open source projects. The company designs and implements programming models, compilers, and tools for multiple vendors. We enable high-performance computing for different markets, including AI and HPC. Our common software stack enables OpenCL and SYCL, as well as supporting SYCL Blast, TensorFlow, and various bespoke work. A little bit about myself. I'm a distinguished engineer with a long history in HPC research and compiler, and recently deeply involved in machine learning, safety systems, as well as autonomous vehicles. Some slides that are going to talk a little bit about various trademarks, but I want to thank numerous people who's helped me with these slides, but I have to claim credit for any and all remaining errors. More legal disclaimers. So let's dive into it. So I like to talk about today three things. I like to talk about oneAPI and SYCL. I want to talk about SYCL 2020, which is just released. And I want to talk about exascale computing with SYCL. So first, I'm going to start by talking about how oneAPI and SYCL are working together to bring developers an open standard environment for developers. oneAPI provides developers with a platform to build accelerated software. And SYCL sits at the heart of oneAPI, providing a mature, open standard interface for developers. When you write code using the oneAPI platform, you will be using the SYCL interface to interact with the low-level hardware on your machine, whether that is targeting an Intel GPU, an NVIDIA GPU, or AMD GPUs. The DPC++ compiler is an implementation of the SYCL standard and makes targeting massively parallel hardware architecture simple and provides you with portability across different targets. The SYCL standard is defined by the whole industry, with myself as the chair, and members from many major processor vendors, national labs, and research groups, ensuring that the standard continues to meet the needs of companies making processors and the software developers who want to easily target those processors. So Codeplay, the company I work for, has been involved in defining the SYCL standard since the beginning. And we have spent many years implementing our own compiler, Compute CPP, which has been focused on delivering SYCL support for customers. We're also closely involved in working on the oneAPI initiative and have been implementing support for multiple processor architectures for DPC++ and some oneAPI libraries. We built partnerships with Lawrence Berkeley National Lab, Argonne National Lab, and Oak Ridge National Lab to enable SYCL on their next generation of supercomputers using the DPC++ open source compiler project. Currently, we are adding support for all the features of SYCL on the Perlmutter pre-exascale supercomputer and continue to extend this to things like tensor cores. We're also working to extend support in DPC++ for the Frontier exascale supercomputer being built for Oak Ridge National Lab. This work is in a development state, but we expect this to be ready for developers to use very soon. You can find instructions to set up DPC++ for CUDA support on this web URL, and AMD information will be coming soon. The compilation steps can't be simpler. Change the target flag to tell the compiler to make the binaries for NVIDIA CUDA target, just as shown in the command in this slide. Now I'd like to talk about the second thing, which is the new release of SYCL 2020 that just arrived. So this is something I'm really passionate about as chair of the SYCL working group. SYCL 2020 is here and is ready for developers to use. SYCL 2020 is released after 3 years of intense work with significant adoption in embedded, desktop, as well as the HPC market. It has improved programmability, smaller code size, and faster performance. It's based on C++17, and it's backwards compatible with SYCL 121. It simplifies porting of standard C++ applications to SYCL, and it has much closer alignment and integration with ISO C++, while supporting multiple backend acceleration and API independence. SYCL 2020, I think, has increased expressiveness and simplicity for modern C++ heterogeneous programming. And what's more, the features of SYCL 2020 have been implemented across multiple SYCL implementations and can be used on real hardware. So I want to point out the incredible SYCL industry momentum in recent years. Most recently, you might have seen the Next platform asking, can SYCL slice into supercomputing? And that is based on the announcement of the collaboration with NERSC, Argonne Leadership Computing Facility on SYCL, on the Perlmutter supercomputer. Before that is SYCL and DPC++ on the Aurora supercomputer. DPC++ is the Intel oneAPI implementation of SYCL, you see on the top right. There is the NSI Tech's Kyoto's microcomputer joint work using SYCL on the RISC-V vector system. There's Tricycle for Xilinx FPGA work from University of West Scotland. There is the Renesas Codeplay collaboration using SYCL and OpenCL on their RCAR ADAS solution. There's the HPC implementation for AMD ROCm CUDA GPUs. And there is the TensorFlow native support on PowerVR using optimized libraries. So what is SYCL 2020? SYCL 2020 is the newest release of the SYCL specification, ratified by the working group in late 2020, published by Kronos in early 2021. It follows SYCL 121, the last version to be based directly on OpenCL. Previous release followed OpenCL-based release, and in light of the move to a more generalized backend model, allowing any backends, as well as following ISO C++ release based on the year, the project has adopted a year-based versioning scheme. SYCL 2020 represents a major step forward, featuring over 40 new additions and improvements, including unified shared memory for pointer-based programming convenience, parallel reductions, workgroup and subgroup algorithms, improvements to atomic operations, class template argument deduction, also known as CTAD, and deduction guides. It simplifies accessors and expands the interoperability with different backends. So this slide is about parallel industry initiative and the possible future roadmap of SYCL. Where we release SYCL 2020 based on C++17, this means it enables exciting C++ features like CTAD and deduction guides that makes code less verbose. There are also a number of other great features which I'm going to highlight. You're going to see that we released SYCL 121 in 2017 and 1.2 in 2015. And if you were to predict, based on past trends, that we seem to be settling down to a cadence of releasing new releases every 1.5 to 3 years, matching to the ISO C++ schedule, you will be correct. This is because we have adapted to a bus train model of delivery. You will also see that we have changed the naming scheme from aligning with OpenCL version to naming by year to allow us to be based on multiple backends in addition to OpenCL, which remains our primary backend. You will also see that we are projecting, tentatively of course, that a future SYCL will be released after 2021, exact version to be named later, and will likely be based on C++20, which will be released, which is already released actually. This shows our tighter ISO C++ alignment, injecting our heterogeneous knowledge into ISO and adapting C++ features. So in this slide, it shows what is in SYCL 2020 on the bottom left. You're going to see some of the 40 features that we have. And in the top box, our general larger philosophy that we have followed in our change from SYCL 121 and SYCL 2020. I remember when we first started this as a workshop called DHPC C++, I know it's a mouthful, and along with the SYCL group, wrote most of the papers and talks 6 years ago. Now we have most talks written by non-SYCL working group members. What a fantastic growth and achievement we witnessed. On the bottom right, you'll see that we have what we have to do next in the form of conformance tests and working on conformance implementations, as well as new SYCL next feature proposals. And on the far right, you'll see that our main goal is converging SYCL and ISO while continuing to strongly support OpenCL, driving to support more kinds of chips. The main diagram illustrates our philosophy of moving from SYCL 2020 to SYCL Next and iterating the cycle with releases every 1.5 to 3 years to the next release. The SYCL ecosystem is open, and there are multiple implementations available for developers. This means that alongside oneAPI and DPC++, there are other compilers available. And the beauty of SYCL is that your source code could compile using any of these implementations. Recently, there's also a new implementation from Japan, NeoSYCL, from the University of Tsubasa on NEC vector offload engine. We'll have a little more about this later. So this highlights the already large and growing SYCL ecosystem, starting with the implementations on the left, including the new NeoSYCL. Then there are the many research papers. Of this, I want to talk about the exascale computing project and Celerity for SYCL cluster. These projects allow SYCL to run on exascale and petascale supercomputer systems and distributed systems. COCOS and Raja C++ are performance portability programming frameworks for C++ parallel execution and memory abstraction. One of our working group members, Nevin Lieber, is working on delivering SYCL on COCOS. GROMACS is a molecular dynamic package mainly designed for simulation of proteins, lipids, and nucleic acids from Stockholm University. That is also a spec CPU benchmark that is now being accelerated for SYCL. The Alpaca library is a header-only C++ 14 abstraction library for accelerator development from Helmholtz and Lawrence Berkeley. TaskFlow is a general-purpose parallel and heterogeneous task programming language, extending for task graph parallelism for distributed and heterogeneous nodes from the University of Utah. The Atlas experiment Athena is a high-energy physics experiment looking for Higgs boson and quarks from CERN. And recently we had 2 talks in GTC 2021. I never thought that would happen, by Brandon Cook of LBNL NERSC and Peter Boyle of the University of Edinburgh. The next column are the benchmarks and books. We have Direct Programming Benchmark, which is a collection of data parallel programs for evaluating oneAPI direct programming. Each program is written with CUDA, SYCL, and openMP. We have SYCL Bench suite, that is a versatile cross-platform benchmark suite for heterogeneous computing from University of Salerno, University of Heidelberg, and the University of Innsbruck. We also now have a oneAPI SYCL book published by James Rinder, downloaded about 385,000 times. With members of Intel's team, all have been good friends that I have worked with some for decades. There are also many libraries for linear algebra, machine learning, and parallel acceleration frameworks, now separated into what domains they serve, including BLAST, FFT, math, random solver, sparse matrix, tensor, and STL. At the bottom, you will see the working group companies attending the weekly calls 1 to 2 times a week. Now I want to talk about the third thing, which is exascale computing with SYCL. So one thing that I've learned from decades of experience working with parallel programming models is that there must be longevity in those that are chosen. There can be a 20-year lifetime gap across a range of supercomputers that need to have a common and standard way to write software. Hardware changes frequently. Look at this diagram, and shows how the US national labs, funded mostly by the Department of Energy, have quite a range of different processor and architectures. What they're recognizing is that they need a programming model that is stable and can support their latest supercomputer. And it needs to be an open standard they are able to influence to ensure it brings the best for developers across their laboratories. These machines cost hundreds of millions of dollars commonly, and their usage spans across laboratories and departments, not only in the USA, but also in Europe and other parts of the world. Now, I worked at openMP in the earlier part of my career, and the first version of the specification was in the late 1990s, and now it's lasted 25 years. And I envisioned the same for SYCL, because it provides the right elements for everyone to develop highly parallel portable software, in addition to using modern C++. Deep diving a bit, let's look at the future for exascale computing across the world. There are over 30 in this table and over $11 billion in cost. These are huge investments. As you can see in the chart below, Hyperion has Japan with its Fugaku post-K system, reaching the exascale milestone first maybe in 2021. In 2022, the United States should have its first two exascale systems, Aurora and Frontier, up and running, and we're involved in those. And at least one exascale system should be up and running in China. The first European exascale supercomputer probably isn't expected until 2023. These data reflect the year the machines are expected to go into production. At least some of these will be installed and running the LINPACK tests for their ranking the year before they're generally available for use. You want to see the current #1 supercomputer? Well, according to the June 2021 top 500 list, Japan's Riken Fugaku is the #1 supercomputer in the world with a high-performance LINPACK result of 415.5 petaflops using a Fujitsu A64 ARM V8.28 processor with 48 out of 50 and 52 compute nodes with GPU-like vector extensions. But there's no actual GPUs in here. It uses a tofu bandwidth, and its peak double precision is greater than 400 petaflops, and its peak single precision can be greater than 800 petaflops. It's expected to have a lifetime of about 8 years. Now, moving on to the US, currently, the current US petascale system are still in the petascale age. And I actually helped deliver one of these called Summit. But looking to the photo right on the graph, you'll see some future systems that are coming up. And I want to look more deeply into those. So here, the exascale plans for the US and China are particularly interesting, in as much as both countries will probably be deploying the largest number of these systems over the next several years. At this point, Hyperion is tracking potentially 6 US-based machines that will go into operations between 2022 and 2025. If the projected performance estimates are accurate, not all will reach 1 exaflop on LINPACK. So for some people, they won't even be considered true exascale systems. Now, these systems, over 2 years, have a budget of $1.8 billion. First one is Aurora, which we're deeply involved in, from the DOE Office of Science and Argonne National Lab. It uses Intel as the prime contractor with HPE and Cray as a subcontractor. Its delivery is in late 2022, acceptance in 2023, and uses a Cray Shasta architecture with Intel Xeons and Intel Xe GPUs. Frontier, also a DOE Office of Science from Oak Ridge National Lab, is also using HPE and Cray as a prime contractor, and its delivery is in 2021 late and acceptance in 2022, using a Cray Shasta with AMD EPYC CPU and future Radeon GPUs. El Capitan from DOE's NNSA's Lawrence Livermore uses HPE and Cray as the prime contractor, and with delivery in late 2022 with full production targeted for late 2023. Cray Shasta architecture is being used with an AMD EPYC processor and next generation Radeon Instinct GPUs. What about China? Let's take closely at the Chinese exascale plans. One of these, more of these, may make the next top 500 list. Wouldn't that be something great? There are 3 prototypes under development. 1 or more prototypes may be selected for follow-up production. One is called the NUDT, which is based on the current Tianhe. It's using an indigenous CPU, possibly ARM-based Phytium or Xiomi, or less likely maybe a Fujitsu A64FX. Okay. It uses a 400 gigabits per second homegrown network and uses an NUDT accelerator. So as such, it's suitable for SYCL. There's Sugon, which uses a heterogeneous architecture with 2 CPUs and 2 DCU accelerators per node. It uses a Hygon processor, licensed clone of AMD's Gen 1 EPYC processor, and an Hygon developed accelerator. Okay. There's also Sunway, which is a CPU-only SW26010 chip follow-on with 260 cores at 3 teraflops per chip. What about Europe? Well, the European Processor Initiative aims to create a new family of low-power European processors, primarily aimed at high-performance computing, the first of which is slated for 2021. The first family, codenamed RIA, will come to market in 2021. It will contain both ARM, RISC-V, and external IPs. It's going to serve as the basis for a European pre-exascale system, and it will also include an automotive proof of concept. EPI also plans to deliver the second family, Chronos, in 2022 to 2023, and it will be using a European exascale system and includes an automotive CPU. So one thing is pretty clear. The effort to reach this level of performance is spurring a lot of new processor developments. The proliferation of general purpose processors and accelerators is particularly interesting. And between the multiple x86, ARM, Power, GPU implementations, as well as the custom HPC processors being developed in China and Europe, there's going to be plenty of diversity and choice for HPC customers, and a greater need for a universal programming language that can switch between all the different vendors. In the next decade, we're going to be expecting that the typical looking HPC systems 5 years from now will now have more than 4 different types of processors in it. And so it's pretty common for something like SYCL to be used, hopefully, as the programming model for these. I'm going to look closely at one example that was published in HPC Asia. We also have exciting news there with a SYCL implementation for the SX Aurora Tsubasa on the NEC vector engine offload, showing no loss in performance from using SYCL in the middle graph versus native VEO offload in the third graph on the Rodina benchmark on breadth first search. It also shows programming with SYCL leads to lower code complexity in terms of lines of code in some cases. So why is SYCL so appropriate for high performance computing when there are already so many other languages like oneMP that's been there for so long? Well, it's because HPC workloads do persist for 20 years, and now it's expanding because to serve the 3 pillars of science problems. One is simulation, which needs an HPC language with solvers and parallel runtime. 2 is data science, which needs a high productivity language for big data. And 3, machine learning, training and inference needs a high productivity language for ML. Now, these have been supported by the top 3 tiers of languages like oneMP, which is mostly for C and Fortran, a mix of CUDA, OpenACC, OpenCL, and now for C++, they are looking towards SYCL, Cocos, and Rajas. This is because the development workflow for these problems starts with 1, choosing an algorithm. And unlike before, today that choice needs feedback knowledge of the system architecture and tools. And those tools need to have control of the data layout, movement, locality, and affinity, or they're going to be non-performant. So SYCL and the other C++ framework enables these parameterization and dynamically configure algorithms through C++ capabilities like templates and inlining. 2, you would implement and test the algorithm. And 3, you would optimize the algorithm. Now, traditionally, this was the only step that needed architecture and tool knowledge. Not anymore. Now you have to know that you have to have that knowledge in step 1 when you're choosing that algorithm. And you now need something like SYCL or C++ based frameworks to be able to dynamically parameterize and adjust that algorithm. Now, all these steps enable us to reach performance portable code. They are required to reach exascale computing for the major systems, of which many are now using SYCL, including ANL's Aurora and NERSC LBNL Perlmutter. The other 2 are AMD-based Frontier systems and El Capitan 10, and SYCL has been demonstrated to work on AMD systems as well. This parameterization and dynamically composing algorithm in step 1, along with compiler optimization, using an open standard programming model is what we think will enable performance portability. So here are some of the SYCL customer quotes using SYCL for HPC from University of Innsbruck, Salerno, NERSC Lawrence Berkeley, and Intel. SYCL can be a part of a standard programming model for all HPC systems, including Europe, Asia, and North America. SYCL is homegrown, EU, UK company led its development since 2012, but now is an open standard with multiple company contributions and lots of European and Asian projects. It moves with ISO C++ and updates every 1.5 to 3 years. It's part of oneAPI. It adapts to high performance computing change, hardware change, and is now moving towards safety critical. It's adapted by the ECP for the first exascale computer in Aurora, now also in Perlmutter, and soon we hope in Europe and Asia HPCs. Thank you. If you're interested to join SYCL, and I'm glad you asked, the membership is open to all, and 3 of these don't need any money, including working on the public GitHub, public contribution space to the specs, and being part of the advisory panel. Only the working group is needed if you want to know the secret sauce of making SYCL. We are now also have an FAQ, which we're keeping up to date on the latest of SYCL. Thank you for listening to everyone. Bye-bye.